In this video, we talk about memory organization. So we know that computer memory consists of a linear arrays of addressable storage cells that are similar to register. Memory can be a byte addressable or word addressable, where a word typically consists of 2 or more bytes. For example, a 16 bits word consists of 2 bytes and so on. So memory basically is constructed of RAM chips, often referred to the term of length times width. So for example, a memory width size of the machine is a 16 bit, then a 4M times 16 RAM chip gives us a 4 megabyte of 16 bit memory location. We're going to discuss later on how the memory is addressed that corresponding to the location of the cell in the memory. So how the a computer access a memory location corresponding to a particular address? So that's gonna based on the way the computer address the memory location. So for example, we can see that for memory storage can be expressed as a 2 to power 2 times 2 to power 20. That's equal to 2 power 22 words. And so the memory location for this memory are number from 0 to 2 power 20 subtract 1. Therefore, in order to address the access to the all the location of the memory, the memory bus of this system require at least a 22 address line. The address line count from 0 to 22 subtract 1 in binary, so each of the line either on or off. This means 1 or 0, indicating the location of the design memory element. So we have the two ways to address the memory location. That's the low order and high order addressing. So we know that the physical memory usually consists of a more than one. To access the memory more efficient, when the memory organized into bank of chip with the address interleave across the chip. So basically, the low order interleaving just means the low order bit of the address specify which memory bank contains the address of the interest. On the other hand, the high order interleaving, the high order address bits specify the memory bank. We can show what does that mean in a few seconds. Let's see here an example of 32 byte of memory where we have 8 modules of each 4 byte each. So in order to address the 32 byte of the memory, we need a 5 bits for addressing, because the 2 power 5 equal to 32. So that's the number of bits in order to address a 32 location in the memory. Specifically, we have the 3 bits for the modules addressing and 2 bits for the offset addressing within the one modules. In the scenario of low order interleaving, so we have the 5 bit for addressing right here. The low order bit right here represent the module number, and the high order bit right here represent the offset in the module. So we have the 3 bit for the module number and 2 bit for the offset in the module. So with that representation, we can see that 32 locations of the memory gonna be represented in a 8 module from module 0 to module 7, where the location gonna be from 0, 1, 2, 3, so on to 31. Okay, so that total we have the 32 locations in the memory. So now, for example, we want to access the memory location or address of 3. We can see that the address of 3 corresponding to the module number 3 and the offset 0. So the module number 3 can be represented by the 3 bit right here. That's gonna be a 0, 1, 1. So that equal to 3. And with the offset 0 right here gonna be represented by the 2-bit right here. That's gonna be a 0 0. Okay, so the location of the address 3 in the memory gonna be represented by 0 0 0 1 1. Okay, so that's the low order interleaving. On the other hand, with the high order interleaving, we use the most significant 3-bit right here represent the module number, and the least significant bit right here represent the offset in the module. So we also have the 3-bit for the module number and 2-bit for the offset in the module. The total number of module we have is we have is 8. So from module 0 to module 7, the same as the low order interleaving scheme. But now you can see that the the location of the memory number differently. So for example, module 0 now have the location 0 1 2 3, and module 1 have the 4 5 6 7, and so on. Okay, the total we still have the 32 location or address of the memory. So now in order to access, for example, we want to access the location or the address 3 of the memory. So you can see that address 3 corresponds to the module 0 and the offset 3. So with the module 0, the bit represent module 0 gonna be 0 0 0. And with the offset 3 is mean a 1 1. So we can see that in order to access the memory with address 3, we use the address of 0 0 0 1 1. Okay, so let's consider another example. Now suppose we have a memory consisting of a 16 of 2K times 8-bit chips. Okay, so the storage capacity of this memory gonna be 32K. That equal to 16 times 2. That's equal to 32K. Okay, so 32K we can be represented by 2 to power 5. Time with 2 power 10. That's gonna 2 power 10 is corresponding to the kilobyte right here. Okay, so that equal to 2 power 15. With that calculation, we can see that the number required to represent the address of memory gonna be 16 bits, right? Because 2 power 15 corresponding to the capacity of the memory, so we need a 15 bit in order to represent every location of the memory. Also, we can see that we have the 16 RAM chip right there. So the number of bits to represent the RAM chip number gonna be 4 bit, because the 2 power 4 equals 16. So we have a 11 remaining bit for representing the offset within a RAM chip. Okay, so the total number of bits still a 15. So here the representation of the memory, we have the row 0 is mean the first chip of the memory. We have the size of 2K, that's number of row, and time 8 is mean the width of the memory. Similarly, we have the row 1 with the capacity to 2K times 8, and so on. So total we have the 16 RAM chip, and each of them have the capacity of a 2K times 8. So the total right here, we have the capacity of the memory gonna be a 32K times 8. That's the memory we want to construct it. With the memory we just constructed, now we try to address every location of the memory. So as we discussed before, we have two approaches: that the high order interleaving and low order interleaving. So with the high order interleaving, we're gonna use the high order 4-bit to select the chips. So basically, here the total number of bit for representing the address of the memory. So we have the 4-bit for the representing the chip number, and 11-bit for representing the offset within the chips. Okay, so the total number of bits is still a 15 bit. Okay, so this is the way the high order bit representation of the memory address. On the other hand, if you use the low order interleaving to represent the address of the memory, so we spend a 4 least significant bit to represent the chip number, and the remaining 11 bit to represent the offset within the chip. Okay, so still again we have a 11 plus 4 equal to 15 bits to represent the address of the memory. So in many scenario, we have the maybe we need to have the multiple chip per bank that we call a word location. This is let's discuss through a specific example. Consider we have a 32 times 16 bit memory where we have only the chip with the type 8 times 8 RAM chip. Okay, so with this condition, we can see that each byte of the memory must appear to be 8 times 16 because the width of the memory is 16, but the width of the and the number of rows of the chip is 8. So we can see that each of the byte gonna be represented by 8 times 16. And 8 means number of row per bank. Okay, here's a bank right here. So we can compute that how many bytes of the memory is needed in order to construct the memory. That's equal to 32 divided by 8. Okay, so that's equal to 4. 32 that's number of row of the memory that we want to construct, and 8 that's the number of row of a one RAM chip. So we can see that 32 divided by 8 is equal to 4. And we also can see that the width of the memory we want to construct is 16 bit, but the width of the RAM chip we have just 8 bit. So the number of RAM chip we need to use, that's gonna be 16 divided by 8 equal to 2 RAM chips. So here's the one bank of the memory. We have the number of row right here is gonna be equal to 8. So that's a RAM chip 1, and the width right here equal to 8 bits as well. Okay, so this is one RAM chip 8 times 8, 8 times 8. Another RAM chip 0 right here, we have the 8 row and also 8 bit of the width. So with this bank, we can see that the concatenation of the RAM chip 0 and RAM chip 1, we can see that the number of row right here is still 8 rows, and the width gonna be 8 bit and 8 bits. So we have the first 8 bit gonna be denoted from 0 to 7, and another 8 bit gonna be from 8 to 15. So the total we can see that the would have the width of a 16 bit. So by using this one, we can construct a memory with the word size larger than the RAM chip width. Okay, so you can see that the RAM the memory width right here is 16 bit, but can be constructed by using a two RAM chip concatenate to each other, so you can construct the width of the word of the 16 bits.